Section 6-5 is on limits of indeterminate forms. And this is called Lhopitals Rule, is how that's pronounced. Lhopital. And the objective of this section is given an expression with an indeterminate form. Find its limit using Lhopitals Rule. So we're kind of going backwards a little bit here, I guess you might say, in the fact that we're jumping back to limits and dealing with limits of indeterminate forms. Now, you've already seen some limits of indeterminate forms. You've already seen 0 over 0 and infinity over infinity, and we've talked about techniques we can use to evaluate those. Lhopitals Rule will give us a technique that we can use to evaluate them in another way. But there are also additional indeterminate forms that we have not discussed. There's actually a total of 7 of these. And so we're going to look at how we can actually evaluate any one of those 7 indeterminate forms. All right, so let's talk about the indeterminate forms. So the first one, we're just going to categorize them here just for, I think, ease of remembering them. So the first 2 here are indeterminate forms that are in the quotient form, and you've seen these 2 already. 0 divided by 0 and infinity divided by infinity. We're talking about working with limits, and when you evaluate the limit, you end up with 0 over 0 or infinity over infinity. We call it indeterminate because of the fact that in the form that it's in, we cannot determine its value. Sometimes these values go to 0, sometimes it's infinity, sometimes it's some number in between. Depends on the problem and the value of x that you're approaching as to what the limit is going to be equal to. The second one here is the product form of an indeterminate form. That if we have infinity times 0, we start out with a product and it turns out that we have infinity times 0. This is an indeterminate form. Now the reason why this is indeterminate because you have the first quantity, which is infinity, and of course multiplying anything times infinity should just give us a huge number. However, the second number is 0. Second function is going to 0. So 0 times anything should, of course, be going to 0. So the first function saying I'm going to infinity, the second function saying I'm going to 0. What is the limit there? It's something, it could be 0, it could be infinity, or it could be something in between. This is why it's indeterminate. You cannot determine its value from that form. You have to do a little bit more work with it. The third one here is what is called the difference form of a indeterminate form. And that's infinity minus infinity. A really, really big number minus a really, really big number does not necessarily give you 0. Could be 0, could be negative infinity, could be positive infinity, or anything in between. And the reason for that is because it depends on at what rate that first function is going to infinity compared to the second function. If the first function is getting significantly bigger than the second function there, when you take the difference, that's going to go to infinity. If they're heading towards infinity at the same rate, then the difference between them is going to be some constant, or maybe even 0. All right, so again, from that form, we cannot determine its value. We've got to do something more with it to determine what value it has. And finally, the last 3 here are power or exponential forms, whatever you want to call these forms here, but 1 raised to the infinite power is an indeterminate form. If you recall, at the beginning of the last section, we introduced you to the definition of what e is, and it was based on a limit, and that limit took on the form of 1 to the infinite power. So in that case, for that function, it turns out that that indeterminate form turned out to be e. But in other cases, 1 to the infinity might be infinity, might be 0, might be some value in between. The reason why this one's indeterminate is because the base is saying I'm heading towards a value of 1, and 1 raised to any power should be 1. So the base is saying I should be 1. The exponent, though, is saying, well, you're taking some number and raising it to a huge power. And when you take some number and raise it to a huge power, you should end up with a really, really big number if the base is slightly more than 1, or is more than 1. Or you should be going to a really small number, 0, if that base is less than 1. All right, if you take 0.1, for example, to raise to a huge number, you get a really small number. Versus if you take 1.1 raised to a huge number, you get a really big number. So the exponent saying I'm either going to be heading towards 0 or infinity. The base is saying I should be heading towards 1. And the question is, which one of those is going to win out here? This is why it's indeterminate. Infinity raised to the 0 power and 0 to the 0 power. Again, you can go through and explain those in a very similar manner to what I just explained here with the first one as to why they're indeterminate. Okay, look at the base, look at the exponent, think about it from one of those two perspectives, and that'll tell you what value it thinks it should be going to. And that's why we say it's indeterminate, because they're different values. All right, so those are our 7 indeterminate forms. Basically, anytime you work with limits and you end up with one of these 7, that's not your answer. You're only halfway, well, maybe not even halfway done with the problem. You got more work to do. You got to figure out what this is actually equal to. All right, so let's take a look at the Lhopitals Rule. Lhopitals Rule, remember, is going to help us find the limit of these indeterminate forms. All right. I'm going to write it 2 different ways here. Actually, they're very similar. Just in this first case here, you'll see that x is going to c. In the second case, we're going to let x go to either plus or minus infinity. It still applies, so you can possibly write it all in one statement. I'm going to just write it as 2, though. It says for Lhopitals Rule, that's how you pronounce it again. Use the right pronunciation for me. Lhopital. Says there, if the limit as x goes to c of g of x divided by h of x is approaching either 0 over 0 or infinity over infinity. And by the way, if there's a negative in there, if it's negative infinity divided by infinity, it's still going to this indeterminate form. You can throw a plus or minus in there, and the result is still the same. In fact, you could factor out that minus sign out front, so you have the opposite of that indeterminate form of infinity over infinity. If that's the case, g of x over h of x is approaching that either one of those quotient forms of an indeterminate. Then the conclusion here is that the limit as x goes to c of g of x over h of x, which is what we're trying to find, is equal to the limit as x goes to c of g prime of x over h prime of x. So in other words, I take the derivative of the numerator, I take the derivative of the denominator, and hopefully that simplifies it so that I can find the limit of that. Now if that turns out still to be indeterminate, then we could use Lhopitals a second time or a third time or how many ever times we need to until we finally get a limit out of this thing. Notice though that we're not using quotient rule here. It doesn't say to take the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. It's not quotient rule. It's just simply saying you have a quotient, the limit of a quotient here, g over h, but just simply take the derivative of the top and take the derivative of the bottom and then evaluate that limit. Now, if, of course, g of x or h of x individually is a quotient, then you have to use quotient rule in the process of finding the derivative of g or in the process of finding the derivative of h. All right? But together, we're not looking at the whole thing and taking the derivative of g over h, but rather it's just the derivative of the numerator, g of x, to get g prime, and the derivative of the denominator, h of x, to get h prime of x. Okay? Now, the second form of this is basically the same thing here. Like I said, all we're going to do is change the value of x that we're approaching. This applies whether you're approaching infinity, negative infinity, or 0. Give us the same result. If we have the limit as x goes to infinity of g over h, and if as long as it's in the indeterminate form for a quotient, 0 over 0 or infinity over infinity, then it turns out the limit as x goes to infinity of g of x over h of x is equal to the limit as x goes to infinity of g prime of x over h prime of x. Notice the whole key to this revolves around the fact that you have a function that's in the form of the indeterminate form of either 0 over 0 or infinity over infinity. If it's not in one of those forms, you can't use Lhopitals on it. Let me say that again. If it's not in a quotient form, you cannot use Lhopitals on it. I stress that because over and over again, I see students that want to take the use Lhopitals on a function they can't use Lhopitals on. So your question might be, well, then how do we handle the other 5 forms? Why do we learn those 5 forms if we don't know how to find the, or if we don't have a method here like Lhopitals to use on it? Turns out that the other 5 forms can all be rewritten in this quotient form, and we'll look at the techniques of how to do that. But if it's any one of the other 5, you've got a few more steps to go through before you can actually use Lhopitals. So actually, if you're in the quotient form immediately, that's nice because you can just jump right into Lhopitals. But if it's not, you've got some steps to follow first before you can use Lhopitals. All right. So we're going to start out with just problems that are in the quotient and product form. We're going to start out with those two. Those two are usually the simpler ones to start out with. Definitely by far the power forms of indeterminates are the most difficult, or actually require the most steps, I should say, to find the limit. So let's take a look at example 1. Example 1 says to find the limit of this function here. So the limit as x goes to 1 of x squared plus 2x minus 3 divided by the natural log of x. All right, now the fact that we're dealing with Lhopitals here might automatically make you think that this is going to be indeterminate, and I guess since it's an example, that's probably a pretty good assumption. However, you need to always check to make sure that you're in the indeterminate form first, and that it's in the quotient form before you try to use Lhopitals. There will be some of these problems where they're not indeterminate. You can't use Lhopitals, and you don't need to use Lhopitals. Just simply evaluate it. Substitute in your value of x, and you're done. So let's check to see what form we are in. If we let x go to 1, in the numerator you get 1 squared is 1, plus 2 times 1, that's 2. 1 plus 2 is 3. Minus 3, the numerator is heading towards 0. In the denominator, natural log of 1, that's the intercept of our natural log function, which is 0. So we end up with 0 over 0. So this is all set up here for Lhopitals rule. All right? So L'Hopital says to do the following. He says take the derivative of just the numerator, x squared plus 2x minus 3. Don't use quotient rule here. Just simply take the derivative of the numerator. So it's going to be 2x plus 2 is the derivative of the numerator. And then divide that by the derivative of the denominator. Now the denominator is natural log of x. Its derivative, of course, is 1 over x. Now sometimes, and in fact I'm going to rewrite this, sometimes you get a form like this that you can simplify before you check to see what value it is. And technically I don't have to do it in this case, but I'm going to go ahead and simplify it, or rewrite it I should say, just so you see that sometimes we have to do this before we try evaluating the limit of this thing. And that is I have 2x plus 2, and I'm dividing by 1 over x. Well, dividing by 1 over x is the same as multiplying by x. So this becomes the limit as x goes to 1 of, I'm going to go ahead and multiply that through here, 2x squared plus 2x. I was able to rewrite or simplify that result that I got from L'Hopital's into this form. And now if you let x go to 1, when x goes to 1, I get 2 times 1 squared is 2, plus 2 times 1 is 2. This is heading to a value of 4. So using L'Hopital's rule, we were able to evaluate this limit. By the way, notice that the problem you started with, it's in that indeterminate form, but it's a polynomial, a quadratic function, divided by our logarithmic function, ln of x. There is no algebraic technique that we have to simplify that limit. The method you have to use here is L'Hopital's rule. And so he takes you through the steps of how you actually evaluate that limit. All right, let's take a look at one more example here. This is going to be an example for the product of an indeterminate, or the indeterminate form of a product here. So let's take a look at example 2. It's the limit as x goes to infinity of x squared times e to the negative x. Now again, I've already said, I guess, that it's the product form, but you can see that we have a product of two functions here, x squared times e to the x, but let's let x go to infinity and see what we end up with. If we let x go to infinity, x squared, taking a big number and squaring it, you get an even bigger number. We call that still infinity. And then e to the negative infinity, if you take e and raise it to the negative infinity power, e raised to the negative infinity, I guess another way of thinking about this, e to the negative x. E to the negative x, remember, is the same as 1 over e to the x, if you want to think of it in that form, if you're not sure what e to the negative infinity is. So here I'd have 1 divided by e to a big number. E to a big number is an even bigger number. And 1 divided by a big number, 1 over infinity, that's heading towards 0. So if I end up with infinity times 0 or 0 times infinity, of course it doesn't matter which order they're in, that's an indeterminate form. That's not the answer. The answer is not necessarily 0 here. Could turn out to be 0. Could turn out to be infinity, or could turn out to be some value in between. It's not until I take a few more steps in looking at this as to whether or not or what value it's actually going to take on. Now, it's not in the quotient form, so before I can use Lhopitals, I have to rewrite it. And this one, with the fact that you have e to the negative x, in fact, my hint there of how to rewrite e to the negative x is probably a hint as to how I can rewrite this as a quotient. But anytime you have a product, you can always rewrite it as a quotient because multiplication by some value is the same as division by its reciprocal. So in other words, I can rewrite this as x squared over e to the x. Now, when you do that, that is because of the fact that it's e to the negative x, I can rewrite that as e to the x and the positive x in the denominator. Whenever you do that, double check to make sure you're still indeterminate. You better still be indeterminate. If you start out as indeterminate in that product form, rewriting it is still indeterminate. So here you have infinity squared in the numerator, that's infinity. Now e to the positive infinity, that's just a big number, that's infinity. So we end up with infinity divided by infinity. That is our form that we need for Lhopitals. So we're all set for Lhopitals. We have the limit as x goes to infinity. L'Hopital says take the derivative of the numerator, 2x, divided by the derivative of the denominator. Well, that didn't change. We get 2x over e to the x. And evaluate this limit and see what it's equal to. If I let x go to infinity, I end up with infinity in the numerator. E to the infinity is still infinity. By the way, if there was anything I could simplify there before I evaluate it, then do so. But there's nothing here I can simplify. I can't cancel out x's, or I can't rewrite this in any other form that's going to simplify it. So I still have infinity over infinity, which L'Hopital says, hey, if you have that form, use my rule. So that's what we're going to do. We're going to use the rule now on this function. The limit as x goes to infinity of, take the derivative of the top, it's 2, divided by derivative of the bottom, which is e to the x. Now again, check to see what form you have here. If I let x go to infinity, oh, check out the numerator this time. It's just a constant, so the numerator is heading towards 2. It's not heading to 0, it's not heading to infinity. It's heading to 2. In other words, at this point, we can no longer use L'Hopitals on this thing. The denominator, though, is still the same. It's heading towards infinity. So I have 2 divided by some big number. 2 divided by a big number is a really, really small number, 0. So in this case, it did turn out that the limit was going to 0. All right, won't always happen that way, though. Sometimes it will be going to 0. Other times it will be going to infinity. And yet other times it will be some value in between. In fact, if I were to take the 2 functions here that I started with, and if it was x to the negative 2 and e to the positive x, then this problem all of a sudden goes to infinity, because e to the x would have been in the numerator. And again, what's happening there, you can see that the relationship between these 2 functions that you start out with here, x squared and e to the x is a function that goes to infinity much, much faster than x squared. X squared gets there, but it gets there way behind e to the x. Okay? I should say it keeps getting bigger and bigger. They both do. But e to the x is going to infinity much faster. And for that reason, the denominator is much, much bigger than the numerator. That's what we see in this last step. The denominator is infinity, but the numerator is just a constant. All right, that's as far as we're going to go here in the first part of this section. You'll have some problems that deal with that quotient and that product form for indeterminate forms using L'Hopital's rule.